So we're Quad A Technologies. I'm Rawan.
Quad A, okay.
I am Khalid al-Subhi.
I'm Noor.
I'm Yasmin.
Are your names up there?
Yes.
Yes.
Okay, let me see.
Right here.
Okay, Rawan. Khalid.
So I'm
Yasmin.
So I'm the CEO of the company. I'm responsible for making executive decisions. Khalid is the CFO of the company. He's responsible for financial affairs. Yasmin is the CTO of the company. She's responsible for scientific and technological operations. And Noor is the COO of the company. She's responsible for developing and sustaining corporate initiatives. And Noor will start us off with giving us an introduction on energy poverty.
Okay, so energy poverty is an ongoing endemic in Africa. It is defined as a lack of adequate modern energy required for cooking, warmth, and other services in schools, healthcare, and workplace. Currently, there are 620 million people without electricity, and this is required for the continent's effort to overcome poverty. Without this electricity, they rely on the burning of dung, charcoal, and kerosene, which are both dangerous and polluting. So this increases the number of deaths linked to indoor air pollution, which the World Health Organization estimates it to be 4.3 million deaths. So who are we? We are Quad A. We're located in Saudi Arabia purely because we're situated in the region and it's easier for us to start up the business there, as well as additional benefits such as cheap rent and low taxes. So our company is focused on research to deliver electricity in a reliable, efficient, and environmentally sound manner. In the future, we hope to see a world where people all over the world, even in remote locations, have access to clean water and environmentally sound house appliances. So our objectives come in twofold: product objectives and social responsibility. The product objectives are included in product development, and so we hope to provide users with a reliable, efficient, and an inexpensive means for clean energy, a place for proper waste disposal, and a process for non-potable water. This ties in with our social mission of creating awareness for energy poverty, the consequences of improper waste disposal, and the need for proper sanitation. In addition, we also hope to assist communities in remote locations with access to energy, waste disposal, and water. And furthermore, we want to help build the Go Green community.
Now moving on to the product, we have looked to several products that we think that are suitable, but we decided to focus on one of them, which is microbial fuel cells, which are electrochemical devices that converts microorganism into electricity directly. That comes with advantages. One, mainly treats wastewater while simultaneously produce electricity. Also, it can function under mild conditions, so there is no changes in the atmospheric of the device. Its application can be applicable in any location that has any wastewater, so it's applicable to any lack of infrastructure, electrical areas. So for this device, it functions as follows. You have two chambers, anode chamber and cathode chamber. The anode chamber has you put in the organic compound, and they react and also they form a biofilm around the anode. Then the electron transfer through the anode through the electric circuit to the cathode, then released to the cathode chamber. It reacts and performs with proton, which transferred through the proton exchange membrane to form H2O. So how all this reaction actually happens? In the anode chamber, we have an anode reaction, which is organic compound plus H2O, forming carbon dioxide and proton and an electron. Then it transfers through the biofilm through three different mechanisms. The first one, direct contact between the bacteria and the anode, and the second is through the nanowires that comes from the bacteria, or by a mediator. Then the electron transfers to the anode through the electric circuit, then goes back to the cathode, where the cathode reaction happens, which is based on oxygen plus 4 protons plus 4 electrons forming 2H2O.
All right, so there are several modifications we have applied to our design in order to reduce the cost of our final product while maximizing its efficiency. So first off, we have completely gotten rid of the second chamber. Typically, when you have two chambers, the cathode is immersed in a solution and it has to be aerated with pumps to provide it with oxygen. The issue with this is that it adds to equipment and energy costs. So by completely removing this chamber and combining it to a single chamber microbial fuel cell, the cathode is directly exposed to air. Therefore, no aeration is needed. The second thing that happens is there's no recycle or chemical regeneration is required of the catholyte. This means that the operation of the device is simplified. And finally, with a single chamber microbial fuel cell, it is easier for us to achieve a smaller cell volume, therefore allowing us to increase the volumetric power density. The second modification we have applied is a cloth electrode assembly. So the position of the anode and the cathode can greatly affect the power output of our system. The closer they are together, the better. However, the issue with this is that as the cathode gets closer to the anode, oxygen diffusion increases. This hinders the main reaction and causes a short circuit in our system. So by applying a cloth between the two electrodes, we are not only reducing the oxygen diffusion rate, but we're also reducing the space between the electrodes for a lower internal resistance and an enhanced volumetric power output. And finally, a catalyst is needed to initiate the reaction. Typically, noble metals such as platinum is required. However, this can be very expensive. So instead, we will be applying activated carbon as our catalyst for its ability to help increase the surface area, which increases the contact between the bacteria and the cathode. It will lower our costs, and it will increase the lifespan of our MFC. All right, so the biggest challenge we face with microbial fuel cells are their very low power density. So there are several modifications we have to apply in order to increase it. First off, research has found that in a single chamber microbial fuel cell, a proton exchange membrane increases the internal resistance of our system. Therefore, by completely removing this proton exchange membrane, we are able to increase the power density 5.2 times. The second thing is the cloth electrode assembly, the CEA. This increases the power density substantially from 3.7 to 627 watts per meters cubed. The third thing we will be doing is we will be stacking our single units of microbial fuel cells in series. This can help increase the voltage by the number of MFCs. So if I'm using two of the MFCs that are similar and I'm stacking them in series, I'm doubling my voltage. And finally, a research group at Penn State University led by Dr. Bruce E. Logan has found that applying activated carbon as our catalyst was proven to be effective in initiating the reaction and increasing the lifespan of our MFCs.
Okay, cloth, is it really an electrode or is it a separator?
The proton exchange membrane,
Is that what the cloth is?
it's
Okay, so that's usually, in batteries I've worked with, you you have an anode coating which
Right.
helps convert from electronic to ionic.
Yes, the proton exchange membrane is the electrolyte separating between the two sets.
Yeah, okay, so it's not an electrode, it's an electrode.
No, it's an electrolyte, yes, you are correct. So there are two governing equations we have been using. First, for the energy equation, we have applied Ohm's law to help us determine the cell's potential voltage, as well as the current output of our system. The second equation we've used was the power law to help us determine the power density of our system. The cross-sectional area over here is the cross-sectional area of the anode. The second governing equation is the mass transfer equation. It is important for us to evaluate the oxygen diffusion rate through the cloth to evaluate its effectiveness. So we've used Fick's first law and multiplied it by the cross-sectional area of the cloth to determine that. The lower the oxygen diffusion rate, the better it is for our performance.
And the cloth, you're going to tell me what the cloth is?
The cloth is a J-cloth that we will be applying.
What's a J cloth?
So J-cloth, typically, if you've seen it, it's the same cloth that you can use when using household appliances. It is super absorbent.
Oh, okay.
Yeah.
So it's a microfiber
Yeah.
cloth.
Yes, it's a microfiber.
But it has to be conductive, right?
It does not.
Or maybe it becomes conductive by absorbing something.
So essentially, it will not need to be conductive because we will have an electric wire that will conduct that electricity externally. That cloth is the sole purpose of the cloth is to decrease the oxygen diffusion rate. So.
But an electrolyte is conductive.
The J cloth is not essentially an electrolyte. In our case, it's not the electrolyte.
So it's an insulator between the
Yes.
anode and cathode.
Yes.
Okay.
And so looking at our product assembly, here's an exploded schematic of one microbial fuel cell. As you can see, we have a cathode, J-cloth, and anode on both sides of the chamber. And the top of the chamber, the opening, is where the wastewater will be coming in. And then looking closer at our diffusion layer, so we're going to be applying the catalyst to the water side of the microbial fuel cell, and then we're applying the diffusion layer on the air side of the microbial fuel cell. And the purpose for the diffusion layer is to decrease water loss and maximize efficiency. How we're going to prepare this diffusion layer is by mixing carbon with polytetrafluoroethylene, and then we're going to apply it on the carbon paper. We're going to let it air dry at room temperature for 2 hours, and then we're going to heat it to 370 Celsius for half an hour. And then here's our overall design of our microbial fuel cell and how it's going to be stacked. There are a total of 26 microbial fuel cells. It may seem like a lot, but it's actually very small. The dimensions are 18 by 22 by 10. And also the space between each row is enough for the wastewater to go into the microbial fuel cell.
Are these like for an individual home or something?
Yes. So the 26 completely will be.
Oh, you mean the
given to each
purpose?
individual home.
So the purpose of, okay, so we'll get into that when we're discussing the market.
And then the overall process, so the first step is we're going to assemble the parts and place them in series, and then we're going to inoculate the microbial fuel cell with wastewater several times to prime it, and also to form the biofilm. Then once it's given to the customer will fill the microbial fuel cell with wastewater at their own convenience, and that begins the chemical reaction. From there, electrical energy is generated and captured, and that electrical energy is used to power a small household appliance, in this case, an LED light.
All right, so let's talk about the market. So currently, it is estimated that the market is worth $9 million, but most of this money is put into research and development. The current leaders of the market are Electrochem Microorganic Technologies, Microbial Robotics, and Cambrian Innovations. As I said, most of it is in research and development. Some startups have received sufficient funding for the production, one of which includes Aviva Aiden's design for a dirt-powered battery, but we haven't found more information on that technology or how it has been furthered. In the future,
the current market is what is being sold now? Or do you mean
the global market?
The potential market, or what do you mean?
As of 2017, the total market is worth $9 million.
Being sold, revenues from sales.
Yeah, I mean, yes, in terms of like paid patents and copyright and those kind of things, but there are very minimal products out there in terms of the market.
Usually when we talk markets, we talk about what the sales are.
Yeah.
Worldwide sales.
I understand.
Well, I guess because most of it is still in research and development, we don't really have, that much information on how much sales it's producing. So.
Okay, well then I don't know what the $9 million is.
It's just the money that is invested.
Okay.
Yes.
The investment is fine.
Yes.
I wouldn't call it a market.
All right.
Okay.
In the future, the market is going to be estimated, or the investments are going to be estimated worth $18.6 million by 2025. And this is promoted or driven by legislative environmental regulations, the need for new water sources, and the non-renewable fuel crisis. So how are we going to target the people? So we're going to segment the market into 3 segments, and this is to concentrate our efforts. So the first being the nonprofit organizations. This is because our main objective is our social mission to help power international communities in need. And so we're going to promote our product to humanitarian and developmental organizations like UNICEF, International Red Cross and Red Crescent, Husk Power Systems, and Selco India. And then we're also going to promote our product to retailers that do camping activities like Raid, Dick's Sporting Goods, and Campmore. So here we're going to promote the product as a clean energy source for camping activities. In the same manner, it's going to be advertised to the general public, who will be able to access our product through the website. And so in order to reach the potential customers, we're going to need several marketing vehicles, which include attending industry conferences, trade shows, vendor events, and also direct emailing and having social networking sites.
Moving on to economical analysis. In the economical analysis, we have put that into two parts. The first part is going to be cost of production, and starting with the revenue and raw material cost, until we get gross margin. We are estimating to sell 5,000 products a year, so that would give us if we are selling a product with $120 by unit, we are estimating to get around $600,000 a year, and also producing byproduct that which is not going to be sold, which is considered a clean water, and and also we will get equipment and raw material cost will be around $360,000 a year, and that will give us a gross margin of around $240,000 a year.
What percentage is your gross margin? Did you figure that out?
Percentage, no, but we've calculated it as the revenue minus the raw materials.
And then
It's
generally you want a gross margin in the order of a large company 80%, 60% is probably the lowest you want to go for with the gross margin. And that's EBIT, earnings before something in taxes. So don't worry, just
Yeah, okay,
that's fine.
sure.
That's fine.
And then going on to the capital cost, we have inside battery limit and outside battery limit. The inside battery limit is based on the renting a lab in Saudi Arabia, Al Khobar, which is cost around $10,000 a year. And the OSBL is 50% of the ISBL, and engineering cost would be 75% of the ISBL. And for the contingency cost, which is a precaution cost that we put in place in case there is an emergency for recall or anything, would be half of the ISBL cost, and that would give us a total capital cost of around $26,000 and working capital of around $32,000. Moving on to the variable cost, which includes the previous and the total electricity. The yearly would be around less than $1,000 a year, and for the variable cost, $361,000 a year. For fixed operating costs, which include labor cost, maintenance, and overhead expenses, which includes zakat and interest on debt financing, which would be around $150,000 a year.
I would actually like to add on that. So he mentioned zakat. Zakat is part of the Islamic law, where we're supposed to donate 2.5% of our profits.
And
What does the person earn? Is that a $25,000 per shift? How many people do you have in this company?
Other than us.
For these?
To assemble them, we have 2 people working on shift. It's a very small lab.
And so you have 6 people in the company?
Yeah,
Basically.
it is a startup.
So you're devoting yourself full-time to this company, right?
Yeah.
Yes, that's good.
What are you earning?
I think so. The minimum wage in Saudi was, I believe, 25,000.
20,000.
20,000,
Yeah.
and then but we were making over that by $7,000.
So you're each earning $27,000, and that's your salary.
Yes.
And your overhead over the salary looks like it's 25 or 40%. I'm not sure what you mean there. I'm not sure. But, for benefits and that kind of thing, it usually runs about 40% over your salary.
I guess because we are a social entrepreneurship, like we're more concerned by giving back to the community. Like our main aim for our company is the social mission rather than revenue. And so that's why our numbers aren't as high as they could be.
So well and good if you have another source for food and
I also know that the government supply and help startup companies with a large amount. We probably did not include that because it's not available data to ask for.
Oh, we also, in Saudi Arabia, we don't have taxes. So all the money that we get is all the money that we get to keep.
Moving on to the profit margin, we are expecting, based on the previous calculated, to get the gross profit of around $92,000 a year, and total cost of production of probably $500,000 a year.
So moving on to the cash flow statement. So the cash flow statement views the cash inflows and outflows over a period of time. As you can see, the simple payback period shows that our return of investment is within a year of production. The return on investment over 10 years is 102%. The net present value calculated using a straight line method with depreciation over 10 years is $149,000, and the internal rate of return over 10 years is 70.5%. These evaluations show a promising future for the company at this production rate.
So now moving on to safety, health, and environmental considerations. After looking at the MSDS sheets for each component, we found out that there isn't major health concerns or safety concerns for each one in terms of corrosion, toxicity, and instability. However, these are our major components. So carbon paper can cause a rash or external ulcers to some individuals. Carbon powder can cause eye irritation and may form combustible dust concentrations in the air. However, it is qualified as weakly explosive, and it can cause some respiratory diseases if inhaled. Copper is very hazardous when ingested and inhaled, and it is also an irritant when it comes into contact with the eyes. And wastewater is harmful if swallowed and inhaled, and proper cleansing has to be exercised right after handling the wastewater. And the safety...
I'm sorry, is copper the electrode? Both electrodes or one electrode?
Is it?
Copper is for the electrical circuit, and the
The
carbon
wires.
paper
Yes.
is used for the electrodes.
Oh, okay.
Yes.
So the safety measures we're going to be taking is that we're going to have all lab personnel and management wear proper personal protective equipment such as lab coats, goggles, masks, and gloves. And then all lab personnel and management have to go through a chemical safety handling training and course. After doing the safety failure mode effect analysis, we changed some of our design controls in our system. For example, we added insulation and a pH detector, just so we don't go out of the range of the acceptable temperature and pH.
Did you choose a critical RP and you want to have something above which you redesign? So you kind of need to have a critical RPM.
I believe we did assess
But
that.
what you're saying that these
So what's
are all
our-
acceptable
Yeah,
in the
yeah,
green?
yeah, yeah,
Okay.
something green.
And then regulation considerations. So since no food or drug is being used or produced during the production of our MSTs, we don't need FDA approval. And then the only regulation consideration we need are environmental considerations. So in Saudi, we don't have as strict environmental regulations as we do here, but us individually care about the environment, so we decided to follow the Environmental Protection Agency's regulations. So the first thing we need to do is to obtain a permit to prove the safe discharge of materials during production. Quad A is also going to outline comprehensive plans with the Ministry of Environment, Agriculture, to manage and regulate our waste once our facility is set to open. And then last, our production process and our product itself doesn't contain any toxic air pollutants, and we don't release any CFCs, so we are in compliance with the Clean Air Act.
All right, so for closing remarks, in the future, Quad A Technologies hopes to further increase the power output of our devices in order to expand its applications for various household appliances. This will include modification of the device and further testing, including altering the shape of the anode to a brush configuration, as it has the potential to increase the porosity and help with the biofilm attachments and electron transfer. The second thing is we would like to add a power management system in order to store the energy and boost the voltage. And third, we'd like to scale up the single chamber microbial fuel cell to increase that power output. And finally, Quad A Technologies hopes to contribute to the wastewater treatment process by applying a scale-up design of our system to create a self-sustained wastewater treatment plant. So finally, giving thanks. First and foremost, we'd like to thank Professor Amit Roy and Professor Thomas Webster for their time and feedback throughout the semester. We'd also like to extend our sincere thanks to our mentor, Larry Siebler, who has given us advice throughout this process. And finally, we'd like to extend our thank you to Dr. Bruce E. Logan at Penn State University for his continued contribution in the microbial fuel cells field. Thank you. Are there any questions?
Thank you. Good job. I have maybe the most basic question is, you have this 24-unit thing that goes in a house and it powers one light bulb. So, and it costs $120. Right?
Yeah.
It costs $120 not for the people in remote locations. That's going to be, yeah, so it's for
subsidized or something.
Yeah, so those are for like the campers or for people that want to use them, that want to buy them for their own use.
We understand that it's a high price at this moment, but I mean, unless there are other investors that are interested in donating to this social enterprise, then we could possibly lower the price. But this is just like
we'd have to continue to evaluate different methods in order to help reduce the cost. But so far, this is the lowest we can get it at.
And then you have wastewater in?
Yes.
Maybe, I'm not sure what, from the toilet or something, probably.
It's provided by the ministry and.
So it's
This is for in a house.
In a house, right.
That thing that's powering one light bulb in a house, and it's powering it by wastewater.
Yes.
And so how much wastewater does that household have to?
It won't need much. It will need just about 65 milliliters. So
Milliliters?
Milliliters, yes.
For all those?
For all 26 of them, so it's very little wastewater.
And then, but it gets used up, it's good, right? And then you need some more
So for
wastewater.
the end product would be clean water.
Okay, and then, but you have to refill it.
Yes.
Yes.
And how often do you have to refill it?
So it'll last for 20 hours before it needs to get refilled again.
Okay, and then the next question is, this biofilm
Yes.
that forms,
Yes.
is it going to clear itself somehow, or is it going to build up?
Right. So it's actually, we need that biofilm to be there. So by providing it with new batches of wastewater, that helps to maintain that biofilm and keep it alive. So it's not growing at a substantial rate where we'd have to remove it or anything like that, but it does keep it there for a good time for it to operate.
How do you know that it's not growing to where it becomes a barrier instead of
Right.
an asset?
Mostly because it takes several weeks to actually first produce the biofilm. If you're working at a continuous rate, that will help grow. However, if you're working in batches, that does just essentially will keep it alive. Yeah.
Those are some of my major questions, I think.
I was not here for the whole presentation.
That's all right. No worries.
Who are you?
I drove in from New Hampshire
Please
this
tell me.
morning. I am Paul Galasso.
Hi. Are you listening?
Yeah, AUB.
Hi, okay. You probably have met.
Yeah, my team's going to present after.
Oh, I see. Okay.
was-
Did you have any questions?
Yeah, that's what I was going to, I'm asking if I can ask a question.
You're more than welcome to ask questions.
Okay.
You're more than welcome to ask a question.
No, so although I did not get the full story. You had commented about the current cost and the need for future work. And one of the things that I find valuable about these projects is that when you go through this very rigorous analysis over the semester, you come up with the results saying, gee, more work needs to be done. Have you been able to sort of identify the areas that are most ripe? If you had funding coming in, where would you apply that funding research-wise to help reduce those costs further?
We would definitely apply it towards, so as we said before, I don't know if you were there for that part, that we need like 26 MSTs to power an LED light. So it's a lot, but they are very little. So if we can find a way to increase the power density without needing as many MSTs, we can reduce the cost. We would use up less money, and so then we would make more money as well.
In addition to that, the best place to invest in that would be scale up. How are we going to scale up this device? Once we are able to scale that up, it will be able to apply to not just a light bulb, it can go into several household appliances, and even in the future, hopefully, we can use this in a wastewater treatment plant.
Okay.
Yes.
You think you're going to be competitive with, I'm not sure what a solar, I know that I've seen a solar panel this big power several things, several light bulb type things, maybe a light bulb and a small refrigerator.
Okay, so I'm going to have my input on that. So I actually worked at a company back home in the Middle East, and they inputted so many solar panels, and it covered probably the whole company, but it didn't generate enough electricity, or even if it did, maintenance costs even more for that.
How do you have to maintain it? Doesn't it just
so
itself?
the weather conditions over there is completely different than over here. These here, I mean, it's not scorching hot.
But not a sand blowing on it.
Yes.
Dust affected.
So I'm guessing this may be another viable method for renewable energy.
In addition to that, it's cleaning the wastewater and it's simultaneously generating electricity. It's doing two things at once, which is very appealing to us.
Can you protect the homeowners when they have to make the exchange? Is there some way of
So there's
hermetically or
so we're providing them with a pump that would, they don't have to get themselves dirty or anything.
Siphon.
It's not
It's
exactly.
like a
It's like
siphon.
a siphon. Yeah.
Yeah.
So.
did you show that?
It's in the costs, but it's not in the assembly or anything.
Well, thank you very much. You did very well.
Thank you very much.
Thank you so much.
You'll get a good grade.
Thank you very much
Thank
for your
you.
time.
Have a nice day.